Okay, so here we go. First problem, and we know in advance, since this is material we covered, that this is going to involve analysis of variance. Well, the thing is that very frequently you'll be presented with a problem, like on an exam, or maybe perhaps as part of your project, where you're going to have to decide which analysis to use, which technique to use to demonstrate that there's a significant finding. In the case of analysis of variance, we're using that where we have a numerical variable and a categorical variable. And the categorical variable has more than one value. I'll give you an example. If we had, it's kind of analogous to the t-test, but it's a bit different in that we have more than one variable in the categorical variable, more than one value in the categorical variable. For instance, if I were going to compare heights of males and females, I'd have two variables. I'd have the gender, whether the person is male or female, and I would have a numerical variable, which is their height in, say, centimeters or in inches. So if I have only two variables, when I go to compare the mean height for males versus the mean height for females, I'm only going to have two averages, two means to compare. And when I have two means to compare, I know I use the t-test. Well, let's say we have a different situation. Let's say that we have a situation where I'm analyzing the data that represents the blood sugar levels of different ethnicities, different ethnic groups within a community. Okay, well, ethnicities, that might have many variables. That might have white, black, Hispanic, Pacific Islander, so on and so forth. So you would have a number of categories. Let's say four. Let's say the four that I just mentioned. So your category variable would have four possible values: white, black, Hispanic, and Pacific Islander. So you got four variables there. So now when you analyze the means of the heights for each one of those groups, now you have four means to compare. Well, t-test only allows you to compare two means. So you need another tool. I have to reapply the t-test multiple times, comparing the Hispanic, blacks and Hispanics, whites and Hispanics, so on and so forth, all of these different groups and all the different permutations, which is unsatisfactory because, if you repeat the t-test over and over again, it increases your chances of making a type 1 error. In other words, finding a difference where there really isn't one. Since your error rate could be as high as 5% each time you run the t-test. So we need another tool. So analysis of variance is that other tool. It uses the variability between the means of all four groups and the variability within each group, and analyzes those to decide whether or not there's a real difference between any of the means of any of the groups. In other words, it's basically kind of doing a t-test for more than two groups. Okay, so that's what we're going to wind up with here. I'm going to start with problem one. I enlarged, I think you should be able to see it at this size. The data file in TC, that's total cholesterol by education. And I've given you a number of different options there: Excel file, CSV file, and there's even an SAV, .sav or SPSS file. And that's the one we're going to use now because it's going to be the easiest one for us to get the results from, and effectively and quickly. Okay, so what do we have here? Well, the data is organized into three values for level of education. Graduated high school is equal to 1, some college is equal to 2, graduated college is equal to 3. So that education variable has three possible values. So we're going to have three means. And the total cholesterol is based on the number for total cholesterol. Okay, we're going to open the file. Let's see if I can find it here behind this. And I'm going to open it up in SPSS. Okay, I have SPSS open already, so hopefully this won't take too long. Okay, and here it is. So here's our data view. You can see down on the bottom here in my data view, I can click my variable view. My data view tells me, I'm gonna go up here to view. I'm gonna turn off value labels so you can see the numbers. So this first individual, his education level was 1, which we know is graduated high school, and his cholesterol level is 200. This person, number 2, is some college, and his cholesterol level was 234, and so on and so forth. These are, this old data, and it's interesting that if you had less than a 200 cholesterol in 20 years ago, you considered in pretty good shape. However, nowadays, boy, at 200 total cholesterol is a disaster. Next thing you know, you're taking pills for 9 times a week. So at any rate, the view of cholesterol has certainly changed quite a view of how aggressively you should treat unsatisfactory cholesterol levels certainly has changed over the last 20 years. So at any rate, let's take a look at this. So now, if I go to a variable view, just to look at the data, you'll see that education, EDUC is the variable name, right? We don't have a label in here for this. I'm going to put in here level of education. Okay, I'm going to put that in there because when I make a table or a chart, what's going to happen in the axis or in the list where it's describing the level of education, it's just going to put that abbreviation EDUC if I don't fill in a label. If I fill in the label, it'll write that entire thing out instead of EDUC. Make the chart a little bit more useful if you want to use it somewhere else. And total cholesterol, well, T cholesterol, I'm gonna actually type in there. I'm going to change that to total. So if someone is reading this, it's a little bit more descriptive. Okay, now as far as values are concerned, if I look at the end here, it already knows that education is a nominal variable. SPSS gives you a number of options here, right? You can have nominal, ordinal, or scalar. Scalar is the same thing as numeric, as most of the other terms most of the other systems that we've used. So we can have a number like cholesterol. We can have a ordinal value like good, better, best, or 1, 2, 3 for levels. And we can have a nominal variable for just a name. Well, this is a name, just a name. It's just going to be the group that we're describing, level of education. Okay, and scalar is going to represent our total cholesterol because it's a number. Okay, so scalar represents a number scale, so we know that that's properly identified. Now, when we have a nominal variable, we know that means we have categories in there. And we can describe those categories if we want to. So we go into values, and we've already done this in advance. Under values for education, 1 represents high school, 2 represents some college, 3 represents graduated college. If I had a 4th value, I would just type in 4 and say other, for instance. Click add, make sure it goes in, and click OK. Now I'm going to remove that because we don't have any other categories. Everybody in there is listed as one of those 3. But that's how we would make sure that SPSS understood what a 1, 2, or 3 was in that column. And we know that worked out because we saw the 1s, 2, and 3s, and we were able to turn on and off the value labels. Now, we don't need values for total cholesterol because that's just simply a number. So we're not going to identify a specific number by a name as we did here with the values. So I'm going to go back to the data view, and just to demonstrate that we really can see that, I'm going to click on the variable labels. And you can see that it understands which ones are which. It uses that information we gave it in the variable view to label these various 1s, 2s, and 3s under this variable education, EDU. Notice if I hover, it gives me the longer name too. Okay, so I'm going to go ahead and analyze this data. At first, I'm going to go back and I'm going to look at my problem to find out what it is that we need to know. What's the problem asking, which is always a good thing, right? Okay, open a file, examine the data, and do the following analysis. Calculate the means and create box plots for each group. So I'm going to go into SPSS again, and I'm going to go into File, Analyze, Descriptive Statistics, and I could go into descriptives. The problem with descriptives is it won't allow me to break it up into different categories. It won't allow me to separate the group graduated high school, some college, and graduated college. So I need to go into Explore. When I go into Explore, my dependence list, my numerical variable is going to go into my dependence list. That's total cholesterol is my numerical variable. You can see it by the little ruler representing it. Okay. My factor list, the groups that I want to break it up into, are my levels of education. Okay, so I'm going to go into statistics, make sure that it's going to calculate my descriptions. It is checked off. And with a t-value of 5% or 95% confidence, an acceptable type 1 error or alpha error of 5%. I'm going to say continue. And I don't have to go into plots necessarily, because I know that when I use Explore, it's automatically going to give me side-by-side box plots. However, I'm going to check off histogram anyway, okay, just to get a look at whether the data appears to be normally distributed. One of the requirements for analysis of variable is that our original data be roughly normally distributed. Okay, I'm going to go ahead and say OK, display both statistics and plots, and I'm going to click OK. Okay, SPSS does the analysis, and we have the data that we're interested in now. First, it summarized the data. There's 44 people that graduated high school in the survey, 27 some college, and 65 that graduated college. And if we look here, we have expansive data statistics about this data set. Here's our mean, 203.77. Okay, cholesterol 203. Some college, 206. Graduated college, 183.65, and so on and so forth. Here's our histograms, roughly normally distributed, and also roughly normally distributed. That looks fairly satisfactory. And here's my box plots. I can see there's a lot of variability here, but I can also see that, gee, it looks like people that graduated college had somewhat lower levels of cholesterol than people that only graduated high school. And some college really doesn't look too different from high school. So based on this, I can see some differences, but there's so much variability. It's hard for me to tell just by looking whether or not that I can say that the differences are due to actual differences for the average of the entire population of people in those groups, or if it's just due to chance in the sample that I took, even though the sample was random. Okay, so one of the things I might do to answer this question is either copy the means and so on and so forth, and paste them in, and type them into our results for our answer sheet for the homework, or I can actually go in here and edit the results. So for instance, I can go in here and take that number and tell SPSS, let me see if I can't find the chart here. Okay, I can tell SPSS that I want to change the color here. Let me see if I can't find the color. Formatting toolbar. Not sure why I don't see it. Maybe it's in here. Here we go. If I click down on that little bar, I can tell I want to make that red. Let's see if it worked. Sure did. Okay, I can do the same thing here. And I can do the same thing here since I want to highlight that data in this chart. Okay, so now that's highlighted, so I know that's the data that I'm really interested in. And if I want, I can edit this chart down so it just shows less information and so on and so forth. Or I could just click on this, say copy, and I can go into my Word document. And under calculate the means and create box plots for each group, and I can say edit. I can say edit. I can say paste. I'm going to say paste special. Now my version of SPSS has a bug in it. Won't let me paste it in as a picture. I like pasting it in as a picture because I do my editing in SPSS, so I really don't need to edit it in Word. I can just have it in there as a picture, which is easier to resize and manipulate and stuff like that. Unfortunately, my version has a bug in it. It doesn't show. Your version should show choices for pasting it in as a PNG file, a bitmap file, or JPEG. Probably it would say also. Okay, I'm gonna have to paste it in as formatted text. I'm going to say OK, and you can see what the problem with that is. It's a very large chart, and it starts to kind of really plant itself near the edge of the page. But you can see it's got the editing that we put in there with the means and so on and so forth. So the lowest mean, as we saw from the box plot, was 183, or the lowest median was 183, was 185 on the box plot. Okay, so the next thing it asks is for us to also show us the box plots. I'm going to go over there and I'm going to click here and I'm going to say copy the box plots, and hopefully I'll be successful with this. But like I said, I have a problem with my version of SPSS. And let's paste in our box plots right here. It'll give me that choice. And format it up. This time it gives me, it recognizes it as a picture. It just wouldn't let me convert it. Okay. See, if it's a picture, I can click on the corners and I can very easily resize it. I can tell it that I want it centered in the page, for instance. It's a lot easier to manipulate. So at any rate, now I have that information in there, which answers my question. See, this one's going to be a lot harder for me to reformat if I wanted to resize the thing. Now, see, it's moving it. Okay, so I'm not going to bother with that. If you guys paste it as a picture, you have a lot more success than I'm having. Okay, so the next thing it asks me is to provide a null and alternative hypothesis. Okay, without naming names, do you want to give it a try and see what would you call what would you propose as your null hypothesis? Each null. Oh, a nice bold italics there. What do you think you might propose as your null hypothesis here? Well, basically, we want to say that the means are all equal, correct? So one way of doing that is just simply typing in and saying the means of all the groups are equal. Or another way of doing it would be to say mu1 is equal to mu2 is equal to mu3. Okay, now we have to propose an alternative hypothesis. Okay, now our alternative hypothesis is that the means are not equal. In our case, we don't care which of the means are not equal. We just want to demonstrate at least two of the means are not equal. I'll just type in all means are not equal. Okay, and sometimes you'll see that phrase another way, like a big, let's say A represents the mean or the average. Large A, 1 does not equal large A, 2, 2 representing all of the different, or B2, or B1, B1, B2, or whatever. A number of ways to phrase it. It's certainly more awkward than it is phrasing a null hypothesis. Or you could also say that the differences are not equal to 0. In other words, the difference between mean 1 and mean 2, mean 2, mean 3, and so on and so forth are not equal to 0. Differences between each of them is not equal to 0. There's a number of ways that you could phrase it, but really, the basic way is all the means are not equal. Okay, so it doesn't matter if mu1 is not equal to mu3 or mu2 is not equal to mu3. They all have to be demonstrated to be unequal for us to have a statistically significant result. Just any two means not being equal. Well, this is a great tool because this means if I have a lot of groups, like let's say I had ethnicity, total cholesterol and ethnicity, and I had 9 ethnic groups, I could analyze all of that data using this one test to examine, is there a difference? And if there isn't a difference, I don't have to go any further. I don't have to analyze each individual pair separately. If there was, say, 9 groups, that would be a large number. It'd be a large number of analyses that we'd have to do. Okay, so I'm going to move on to the next part. Perform an analysis of variance using your choice of methods. Excel, SPSS, and R. We're going to use SPSS, of course. Paste in the table. If you want to use something else, we have an Excel file there. We have the .csv, a comma delimited file that you can use with R and so on and so forth. But I'm going to use SPSS for our purposes. It's going to be easiest for us to complete. Analyze. Now, what are we doing? Even though we call it analysis of variance, we're comparing means. So I'm going to go into compare means. I'm going to go into one-way analysis of variance. And I'm going to tell it the dependent, again, is the numerical variable, which is total cholesterol. The factors are the groups we're going to break it up into, which is level of education. And I'm going to go ahead and click OK. Now, there is something here called post hoc test, but I'm going to get to that in a moment. I'll click it, get back. It brings back our output table, and here's our analysis of variance. Now, as you guys may have remembered from when we did this in class, the mean, we have the sum of squares of the differences between the groups, and we divide that by the degrees of freedom, the number of groups minus 1, 2. We get the mean sum of squares, and between the groups, we get the mean sum, same process, except we do it for within the groups. We get the mean sum of squares within the groups, and that's the total number of individuals within all of the groups minus the number of groups, 136 minus 3. Divide that into 175,000, and we get the mean sum of squares. And our F statistic, our analysis of variance statistic, is the mean sum of squares between the groups divided by the mean sum of squares within the groups is 5.749. If we don't have SPSS, we would analyze this using a table of critical values for the F score. Okay, and we would decide we reject our null hypothesis and accept our alternative hypothesis if the F score we got exceeds the critical value. I'm not going to go to the table because SPSS actually has calculated for me the probability that we would be wrong if we reject the null hypothesis. In other words, the probability of making a type 1 error. And that's 0.004, 0.4%. Okay, we're willing to accept a level of error of 5%, 0.05. Since this, our probability of being wrong is less than our acceptable level of error, alpha equals 0.05, we reject the null hypothesis because we know that we're probably not going to be wrong if we do that. And we accept the alternative hypothesis. Okay, so I got a little ahead of myself there because I think that's going to probably be the next question. So I'm going to copy this, and I'm going to paste it in to our analysis. Okay, paste in the tables below, and I'm just going to go ahead and paste that in. What's the p-value or significance of your test? Well, p-value, p, is equal probability of being wrong if we reject the null hypothesis is equal to 0.004. Do you reject your null hypothesis? Yes, we reject it because our significance or probability of being wrong, making a type 1 error is less than 0.05. Yes? Whoops, excuse me. P is less than 0.05. It's hard to see that 0, so I'm going to put 0 in front of it. Okay. If you find statistically significant difference, perform a post hoc test. And we gave a choice Bonferroni, a Tukey, and so on and so forth. In other words, now we've demonstrated that there is a difference between the means of at least 2 of these groups that we're examining. So now I'm going to go back and I'm going to apply these after the fact tests, post hoc tests, to determine which of the groups are likely to be different. So I'm going to go up here to analyze. Notice I don't have to go back to the data view if I don't want to. I'm going to stay with the output window for now. Analyze, compare means, analysis of variance, except this time I'm going to click into post hoc test, and I'm going to ask it to go ahead and do the Bonferroni test. Okay, and that's going to re-examine all of these different combinations of groups that you might be comparing to each other. I'm going to click continue. I'm going to say, okay, it repeats the same analysis. Get the same table we did before for the F score, but now it's actually looked at. Well, let's compare graduated high school with some college. What is the significance there? Well, no, that's greater than 0.05, so that doesn't seem to help. How about graduated high school versus college? Oh, well, the probability of being wrong, see significance, remember that's our p-value, probability of being wrong if we reject the null hypothesis. Well, in that case, it's less than 0.05. Well, how about some college versus graduated high school? Well, note that doesn't work. We just did that same analysis up here. Notice it repeats all of them twice. Okay, some college versus graduated college. That difference is significant. So we have two areas of significance here. One is graduated high school versus some college. That can be easy for me to do that. Okay, I'm just going to leave that the way it is. Graduated high school versus some college versus graduated high school versus college. Graduated college is significantly different. So we reject the null hypothesis for that. And graduated college versus some college versus graduated college, we reject the null hypothesis for that. We don't reject the null hypothesis for graduated high school, some college and graduated high school. The difference there is not enough. The variability between the groups and the difference between the means of the two groups is not enough for us to reject the null hypothesis that the means are the same for that pairing. But you see the summary table, we actually have them all in there at the same time. Actually, I can get away with highlighting that one because they happen to be in the same box. Okay, in this case, graduated high school, graduated college, there is a significant difference. Graduated college and some college, there is a significant difference. So I'm going to take this table and just paste it in, but you can also put that into words as well. Okay, and okay, I'm going to paste that in here just so we have it. And I'm going to go back and answer the questions. Is there a significant difference in average cholesterols in this population for men who graduated college versus men who graduated high school? Yes. Our answer is yes there. There is a significant difference, right? And if you want, you could put in the p-value. P, I think that was equal to 0.0. What was it again? It was 0.016. And graduated college versus some college. Let's see, graduated college versus some college, 0.022. Yes, there is a significant difference. Equals our probability of it being wrong. I have any type 1 error by saying that's true. It's 0.22, 2.2%. How about some men? How about men who completed some college versus men who completed high school? Well, no. We failed to reject the null hypothesis. That the two means, there's a mean for men who completed some college versus men who completed high school have different average cholesterols. That one we can't reject the null hypothesis for. Yes, we can for this pairing. This we can for this pairing. No, we can't for this pairing. Okay, so that's basically where we stand with the technique that we're using with analysis of variance. Let's apply it again to this next problem. Okay, problem 2. A researcher is concerned about the level of knowledge possessed by university students regarding United States history. Students completed a high school level standardized history test. Majors for students also recorded. So we have 4 columns here because it's listed a little bit differently than SPSS would. We have 2 variables. We have the major that the student has. Each student has a major on one of these 4, and they have the score that on this history test. Okay, let's open the data file for this particular test. I'm going to minimize that, and I'm going to go back here, and that's going to be problem number 2. And let's see which is the most recent version of this. I'm going to open that one up. Okay, and here we go. Again, we have a numerical variable, happens to be in the first column this time. We have a categorical variable. And we have this time, this time instead of 3 categories, we have 4 categories. But the procedure is going to be basically the same. I'm not going to bother to fill in all of the answers the way we did, because basically we're asking the same questions as we did before. First thing I'm going to do is I'm going to analyze, descriptive statistics, explore. And I know that if the question is the same, questions are the same as before, I'm going to put the score, which is our numerical variable, into the dependence list, the major into our factors. I'm going to just check. It's going to do our statistics. That's checked off. Good. And I'm going to have it do a histogram right off the bat because I know I'm going to need that anyway. I'm going to click OK. SPSS. Now, notice it uses the same output sheet. Okay, I'm going to look at it. Now, I've calculated my means, 56, 53, 53. Let's see, 53.125. They seem very similar, don't they? But, let's see, is there much variability between these? Confidence interval is pretty wide there. Well, let's go ahead and analyze this. I'm not going to speculate on it. Doesn't look quite as normally distributed as, whoops, did I do something wrong here? Those are my frequencies. Oh, I thought I asked for histograms, didn't I? Oh, it broke the plots up into what might have been more interesting if we had more categories here for the scores, broke them up into different score ranges. But boy, these box plots look awful similar, don't they? The medians look a bit different, but there's a lot of variability here. So I'm wondering whether or not I'm going to be able to demonstrate a difference here. But we're going to go ahead and do our analysis. So I'm going to go up here to Analyze, Compare Means, One-Way Analysis of Variance. And again, my dependence list is going to be the scores on the test. My factor is going to be the major, students' majors. And I'm going to go ahead. Actually, I'm not going to run post hoc tests until I know there's a difference. That would be a bad practice, I think. So I'm going to click OK. And let's see what we wind up with. Oh, my goodness. Let's take a look at this. Our F score is 0.057. It's a small number. And our significance is 0.982. There's no significant difference between any of these four means. So my null hypothesis would have been the mean for let me see, the mean for education majors equals the mean for business majors equals the mean for behavioral science majors equals the means for fine arts majors. That's our null hypothesis. I failed to reject that null hypothesis because I haven't demonstrated that there's a big enough difference between those three means given the variability within the groups. Okay, so I think I just did problem 3 instead of problem 4. I'm not sure. Instead of problem 2. But I'm gonna close the output. No, maybe not. Let's leave it open. Okay, let's do the next problem. So you would then answer all the questions and you would not bother to run the post hoc test, right? Because you haven't demonstrated to start off with that there is a difference between the three groups. Value for what's your degrees of freedom? Is there a significant difference between any of the first 4 tests? Actually, there's 2 degrees of freedom there, right? There's going to be degrees of freedom between the groups and degrees of freedom within the groups. But you know where to get those off the table. Which of the groups exhibit a statistically different difference? Well, none of the means are statistically different. So you would say just simply no, and you wouldn't run the post hoc test in that case. Okay, let's take a look at 3. A simple random sample of cars on a highway are randomized to be exposed to one of 4 methods of speed reduction. Put up a speed limit sign, put up a sign plus sign saying speed limit strictly enforced, put up speed limit sign plus speed radar control, and finally speed limit sign plus an empty patrol car parked on the side of the road. This is the data for the speeds of cars that went by in those different situations. Okay, so we're going to apply analysis of variance, right? And our alpha is going to be equal to 0.05. Our acceptable level of type 1 error is 5%. And we're going to state our alternative our null hypothesis that there's no difference between the mean speed for each of these 4 categories. And our alternative that there is a difference between in the mean speed in at least 2 of these categories. My degrees of freedom, we're going to calculate that. The F statistic, is there a significant difference? And which of the groups exhibit that statistical difference? Okay, so I'm going to go back to my analysis of variance. I'm going to open up this. I'm going to open up my other file. Okay, and here we go. Sign only, speed limit, sign radar, and so on and so forth. I'm going to do my analysis, analyze, descriptive statistics. I'm going to do my descriptive statistics first just to get a look at it, explore. Speed is our numerical variable. Method of speed control is going to be our factor. I'm going to ask it to do a histogram, and I'm going to click OK. Okay, sign only, the average speed was 64 miles an hour. Speed limit strictly enforced sign, 61 miles an hour. Speed radar control, 57, and a patrol car on the side of the road, 55. So it does seem like there's a difference. My histograms, I can use them to examine whether I think the data is remember, these are small data sets we're using. So in real life, you work with bigger data sets, and it's a little easier to tell whether it's really normally distributed or not. There are numerical tests. We haven't dealt with those so far this semester, but visually, we can use the histogram to kind of get a judgment about that. But usually, again, you're working with larger data sets. Hard for us to see that with these small data sets. Now, in this case, with the bar charts, it does look like I can see a difference between these different groups, can I? The variability is, quite a bit less. There's quite a bit difference between the patrol car and the sign only over here, isn't it? Now, the question is a big enough difference to make up for the variability in the data? And what about all these others? Are they different? Is sign only different than sign with an extra warning, or sign only and radar, and sign only, and so on and so forth? Okay, so we're about to analyze that. I'm going to go up to Analyze, Compare Means, because again, we're comparing the means of the average speed rates. One-way analysis of variance. The dependent variable is speed, the numerical variable. The factor is the categorical variable, the different methods. I'm not going to run the post-hocs until I know that I have a significant difference between at least two of the averages for these four groups. I'm going to click OK. And my analysis of variance is complete, and my F-score, my analysis of variance, is 5.11. We remember that for a small number of groups like this sounds like it might be significant. And indeed, the p-value, the probability of being wrong if we reject the null hypothesis, is 0.004. It's a lot smaller than 0.05. So we reject our null hypothesis that the means of all of these different groups are the same. And we accept our alternative hypothesis. Now the question becomes, which of the groups are different? Okay, and for that, we go back into Analyze, Compare Means, Analysis of Variance, and I'm going to go into Post-hoc Test. I'm going to use Tukey this time, okay, or no other reason than I feel like it. And I'm going to click Continue, and I'm going to click OK. And we get our results. And each one of these different groups is compared. Sign only compared to strict enforcement versus speed radar control. That is kind of borderline, isn't it? Sign only versus empty patrol car. Well, that's definitely significant. Okay, well, let's see if we see any other significant results. Well, speed limit versus sign only, nah. Speed limit versus speed radar control, nah. Empty patrol car versus speed limit strictly enforced, no, not a big difference. Speed radar controlled versus sign only. Well, that's the same result we got up here, right? They just reversed. Sign only versus speed radar controlled. Speed radar controlled with sign only. Obviously going to be the same result. So we know about that already. So if I want to summarize this, I would say, well, there's a significant difference between sign only and, since it's so close, I'm going to reject the null hypothesis for this. I'm going to make a judgment call and say, yeah, that's acceptable. There's a significant difference. I'm not going to be hard-headed about it. Sign only versus speed radar controlled. I'm going to reject the null hypothesis and say there is a difference. Sign only versus empty patrol car, significant difference. And speed limit strictly enforced and speed radar controlled seems to be a significant difference. The others don't exhibit a significant difference, so I'm not going to say that they're different. The other possibilities, okay, of which there are a total of 6. 3 out of the 6 comparisons give us a result that says we can reject the null hypothesis, okay, because they gave us a result, the probability of being wrong probability of a type 1 error of less than 0.05, or in this case, almost exactly 0.05. Okay, so that's basically how we would solve each one of these three problems. So how do you feel about that? Does that make sense to you? Is there any part of that that like wasn't clear that I need to go over again? Okay, good. Were you able to submit it yet, or are you still working on it? Oh, okay, good. Well, I hope this, was kind of a good backup to it. Let's take a look at homework, at the homework 5D, the newer homework. Just a quick look at it to kind of prime things, to get things ready here. Okay, and let me just, okay. Now, in chi-square, we're working with a somewhat different situation now, aren't we? We're working with a situation, let me just click on this and save this file on my desktop so I have it for us to work with. In chi-square, we're working with a situation where the variables that we're examining are both categorical variables. For instance, let's say we wanted to determine whether or not gender has an association with having diabetes or not. Okay, so we survey, say, 100 people, and half of them are males, half of them are females, and we determine that 50% of them we ask each person, we record their gender, we ask them if they've ever been diagnosed with diabetes. In fact, you can get this very information from the New York City Health Survey. You can actually go in there and download a random sample. I think it's a phone survey, a random sample of thousands of people that were surveyed for various conditions and lifestyle choices and physical characteristics and so on and so forth. For instance, gender is there for sure, and whether or not they've ever been diagnosed with diabetes is there for sure. You can actually compare this with some real data. Okay, but in our case, let's see. In our case, our case, what we're looking at is a slightly different, a different analysis that involves both categorical variables. There's no numerical variables here. There's no measurement variables. In this case, we're looking at, let's see, problem. Let's see which is a good one too. Okay, I just asked you to do that. In this case, we're looking at stenosis. Stenosis is hardening of the arteries or a restriction of coronary arteries. Okay, so we're looking at stenosis. And this study examined 215 smokers and non-smokers. So one categorical variable is smoker or not smoker, one or two, right? The other categorical variable is, did they exhibit symptoms for stenosis? Yes, they did. No, they didn't. So the way that we organize this data is into what we call a contingency table, since it's categorical variables. Okay, so I'm going to open up that data set that I just stored on my desktop, and hopefully I'll be able to find it. Let's see, there it is. Good. Okay, and there's our data. I also have data on gender, for instance. Here's my data on disease. They have stenosis or they don't. And smoking status. Are they smokers or are they not smokers? So, I'm gonna analyze. I'm gonna go to descriptive statistics, and I'm gonna go down to something called crosstabs. Crosstabs is basically this idea of organizing this data into tables, into what we call contingency tables or crosstabs. So usually I like to put the exposure in the rows and the outcome, like disease or no disease, in the columns. Okay, kind of mimics what we did with the diagnostic testing, right? We always put the disease, yes or no, on the columns, and we put whether a diagnostic test was correct, was positive or negative in the rows. So I'm going to put the exposure in the rows. Smoking is the exposure. I'm going to put that into the rows. The presence of aortic stenosis, well, yes or no, do you have it? That's the outcome. I'm going to put that into the columns. Okay, so now, at this point, I'm not going to run any statistics yet. All I'm going to do is I'm going to go into cells here, and I'm going to make sure that it's recording the observed values. Okay, see, the only thing that's been checked off so far is observed values under the cells. Okay, so I'm going to click OK and see what kind of output that gives me. Well, here's my output. My output is that it organized all of these ones and twos, for stenosis and for smoking into this group. How many people do we have that smoke? Well, we have 96 smokers. 53 of them exhibited stenosis. How about non-smokers? Non-smokers, we have 119 non-smokers. 47 of them exhibited stenosis. Okay, so, I'm satisfied with that organization now. I have 100 people that have stenosis, 115 in this particular population. Obviously, maybe it's an elderly population, maybe it's a population of patients that are already in a hospital for other reasons, and so on and so forth, right? So, because of a pretty high rate of stenosis here, right? So, at any rate, so now I have this organized in a way I can kind of examine it. Okay, so I'm going to go a bit further with this. I'm going to go up to Analyze. I'm going to go up to Descriptive Statistics. Excuse me. I'm going to go up to, Descriptive Statistics, crosstabs. And I'm going to go back into cells. And this time, I'm going to ask it to calculate the percentages by rows. Click rows. I'm going to say Continue. And I'm going to say OK. Well, this time what it did is it calculated, 53 people that smoke have stenosis out of 96. So that's 55% of the smokers have stenosis. How about the non-smokers? 39% of the smokers have stenosis, out of 100. Well, in fact, we have measures of risk that we can describe two ways. We can describe it as risk and relative risk, or we can decide it as odds or odds ratio. If I look at this data right now, the risk of having stenosis if you're a smoker is 53 over 96, or 55%. The risk of your having stenosis if you're a non-smoker is 47 over 119, which is 39%. Now, the relative risk, in other words, the ratio of the two risks, is 55% over 39%, which is roughly, I'm going to say 1.6 or 1.7 or something like that. In other words, you're 1.6 times as likely to have stenosis in this population if you're a smoker than if you're a non-smoker. That's relative risk. The other way you can see calculating that, instead of using the percentages, is 53 divided by 96 over 47 divided by 119. That would be the same thing as comparing the percentages. Odds works a little bit differently. The odds of having stenosis if you're a smoker is 53 over 43. And the odds if you're a non-smoker is 47 over 72. The number of people that don't have it versus the number of people that do have it for that given exposure. Okay, and you would calculate an odds ratio the same way as you did the relative risk. You'd find a ratio of those two odds. 53 over 43 divided by 47 over 72. Very frequently they come out similar, but not exactly the same as the relative risk. Various reasons for using one or the other, but many studies take advantage of these kinds of descriptors, these kinds of statistics to describe the increase in risk or the increase in odds of getting ill if you have a certain exposure. Okay, so I'm going to go back up here, Analyze, Descriptive Statistics, crosstabs, and I'm going to go back into cells, and now I'm going to do another calculation. I'm going to check off expected values. I'm going to uncheck percentages just to make the tables a little simpler. I'm going to continue and click OK. Okay, so now what SPSS has done for me is it's figured out, well, the rate at which people are getting ill is overall within this population is 100 over 215, or about 40% of the people are getting stenosis. Well, it said, well, if there's no difference between smokers and non-smokers, I would expect 40% of the smokers to get ill and 40% of the non-smokers to get ill. Well, in fact, the rates are different. We saw that in the percentages. They're not the same. So what SPSS does is it calculates expected values for each one of these cells. And the expected value, had there been no difference between smokers and non-smokers that we would have seen in aortic stenosis, would have been 44 versus 53. So more people are getting ill than we would have expected. So now that makes us suspect there's an association between smoking and aortic stenosis. And it looks like fewer people are getting ill than we would have expected for non-smokers, right? Again, maybe there's an association between smoking or not smoking and stenosis, right? But now we have to analyze this. The way we analyze this is we calculate a statistics called chi-square. And chi-square is calculated by taking the, basically, okay, there's a greater issue here. So there's other issues here that involve the number of variables in here and a correction called the continuity correction. But usually for very large sample sizes, we're pretty comfortable. And these are pretty big sample sizes. So the way we calculate is our chi-squares for each one of these boxes. We look at the expected values and the observed values. We take the observed value minus the expected value. We square it and we divide by the expected value. Put that number aside. We do the same thing for each pair in these boxes, the differences between the observed and the expected, and we add those numbers together to get the chi-square value. So I'm going to go to Analyze. I'm going to go to Descriptive Statistics, crosstabs, and this time I'm going to go into Statistics, and I'm going to ask SPSS to calculate the chi-square for me. I'm also going to check off risk, because I'm going to need that also later on. So I click OK, and OK, and now we have our calculation of chi-square. So here's our calculation of chi-square. Our chi-square value comes up to be 5.273. Now, if we're not using SPSS, we would now go to a table which compares the critical value of chi for the number of degrees of freedom. Degrees of freedom for this analysis are 1. That's determined by the number of rows and the number of columns. It's the degrees of freedom are the number of rows minus 1 times the number of columns minus 1. Well, it's 2 rows minus 1 is 1. 2 columns minus 1 is 1. 1 times 1 is 1, so the degrees of freedom are 1. We go to a table where we can look up the critical value of chi-square and see if our value of 5.2 exceeds that. I happen to know that it's somewhere around 3.8, so it does exceed it, but I don't even really have to know that because SPSS calculates my p-value or probability of being wrong if I reject the null hypothesis. We didn't mention null hypothesis yet, so I'll get to that in a second. So the null hypothesis, well, maybe I should bring it up now. The null hypothesis is that there's no association between smoking and the presence of aortic stenosis. And the alternative hypothesis is that there is an association, that these numbers are different, the observed numbers are different enough that it's not, that the differences are not due to chance. Okay, so in this case, my p-value is 0.02, which is well under 0.05, which is my level of, my acceptable level of error for a type 1 error. Okay, so since 0.02, my p-value significance, as SPSS calls it, is less than 0.05, I reject the hypothesis that there's no association between smoking and aortic stenosis, and I accept the alternative that there is an association. Well, I also am going to look at my values for my risk ratio and my odds ratio. Well, right here it says my odds ratio for smoking status, yes versus no, is 1.88. That's, I estimated that at 1.6. I was off quite a bit. Right, it was 1.88. That's the number that we calculated for the odds ratio. Okay, that came out to be 1.88. If there's no difference between smokers and non-smokers, I would expect the risk to be the odds to be the same for smokers and the odds to be the same for non-smokers. So I would expect the odds for smokers divided by the odds for non-smokers, the odds ratio, to be 1 if there's no difference between the two of them. So we want to see if that difference, 1.88, that odds of almost twice the odds for smokers, is that real or is that just due to chance? Well, our assumption is, our null hypothesis is that it's equal to 1. The odds ratio is equal to 1. But we want to be 95% sure, have less than 5% chance of a type 1 error, that they really are different. And SPSS calculates a confidence interval. Well, our odds ratio for this sample was 1.888, but our odds ratio, 95% confidence interval for the odds ratio for the entire population is 1.09 to 3.25. Notice that our 95% confidence interval doesn't include the ratio 1. So we can be 95% certain, basically, or less than 5% chance of being wrong, that the odds ratio is different than 1 and that there is an association between smoking and non-smoking. Similarly, the risk ratio was 1.4, 1.398. And let's see if that's different than 1 as far as our confidence interval is concerned. And yes, it excludes the number 1. So that all three ways of examining this data, the risk ratio, the odds ratio, and chi-square, all agree that we can reject the null hypothesis and say there is an association between smoking and lung cancer. Okay, so if I was looking at my problem that I had to solve, organize the data into contingency tables, we did that. Calculate the expected values, we did that. Calculate the percentages by rows, we did that. State your null and alternative hypothesis. Report the chi-square value. What's the p-value for that? Do you reject your null hypothesis? We sure do. What the relative risk? What 95% confidence of the relative risk? State your null hypothesis for the relative risk that's not equal. Null hypothesis is that it's equal to 1. Alternative hypothesis is that it's not equal to 1. Do you reject your null hypothesis? Sure do. And report the odds ratio, and we did the same thing with the odds ratio there. Okay, the second problem just asks you to interpret tables that have already been produced for you. So, and you'll have to figure out which of these is chi-square and which is significance, and you can go back and replay this if you don't remember which columns or groups to use here in order to tell what's going on. One interesting thing is that the odds ratios are less than 1, not greater than 1. They don't include 1 in 95% confidence intervals. I'm thinking we're going to reject the null hypothesis. But what does this mean, having an odds ratio and a relative risk of less than 1? Okay, what does that mean? I want you guys to think about that to determine that. Okay, so I think that should get you going on the second part of this thing if you're having problems or you're hesitant about it. But remember, the real key here is that we now have a test for comparing the means of two groups, t-test. We now have a test analysis of variance for comparing the means of multiple groups at the same time. We now have a way of analyzing data that is, in both cases, is categorical data, right? Two categories or two nominal data. And next week, we're going to have a mechanism, correlation and regression, that'll help us to evaluate whether there's an association between two numerical values, like, for instance, blood pressure and age, two numerical variables, where we don't have a categorical variable to compare means. We can't compare mean age and mean blood pressure because they're two different things. But we can look to see if there's an association between a person's age and his blood pressure, two numerical variables. So we'll take a look at that then.